Welcome. In this video I'll go into a bit more detail about how fixed boundary Grad-Schiff-Farnoff solvers work. So this is the Picard iteration of solving the nonlinear problem to turn a nonlinear problem into a linear problem, and then how the boundary conditions are imposed, a bit about the flux surface and coordinate mapping used in the solvers, and then the finite basics of the finite element method. Obviously I can't hope to cover this in one short video, but I hope this is enough information that you can look up the details if you need to look at them up. Okay, so the first one is the basic Picard iteration, and this is a way of solving a nonlinear problem. So the Grad-Schiff-Farnoff equation has two parts to it. So there's the left-hand side, which is the linear part, is an elliptic operator, sometimes called delta star. So this is an elliptic operator, so r is the major radius and z is the height. And then on the right-hand side, there's a function of r and z, which is essentially the toroidal current, where f and p are functions of psi. This is the pressure and the poloidal current functions. So this contains all the nonlinearities, because these depend on psi, and then psi depends on pressures and f. So in order to solve this problem, that we need to know what this is in order to calculate psi, and we need psi in order to calculate what this is. So what we do is have a Picard iteration, choose psi naught. So psi naught is some function of r and z. This is just an initial guess as to what the solution might look like. We then put this into calculate this f. So by using the inputs or specified these input functions, so we know what p as a function of psi and f as a function of psi are. This lets us calculate something as a function of r and z. And then once we have this, we can then solve for the next one. So we have psi. I'm going to label the index here as the iteration number. So this is n plus 1. And we're going to solve this by inverting this operator. So calculate this as the inverse. So inverting this, and it's a function of f. And it's f, which is a function of psi n. So if we can label psi n here as the iteration n, we calculate psi n plus 1 by inverting this, and then this goes back into the start. But first we can check for convergence, and typically the way we do that is by checking the maximum change. So we'll check psi n plus 1 minus psi n, and look at the maximum. So what's the maximum difference between these two? If it's smaller than some tolerance, so some small tolerance, then we say we're finished. But if psi is still changing between iterations, then we go back. And from this new psi, we calculate the new f, and then solve it again. And we keep iterating until it finds convergence. And this is the Picard iteration. There are other methods as well we could use. So Newton iterations also work. So Newton iterations are used in some codes. A downside of Newton iterations is that they need to be close to the solution in order to converge. So if the solution is too far away from its final result, you'll find that the solution diverges and doesn't converge. Whereas typically the Picard iteration tends to be more robust. So one option is to start with the Picard iteration and then use the Newton iteration once you're close to a solution to accelerate to converge faster. But typically Picard iteration is good enough. One problem which can occur is that you can end up with solutions which oscillate. So when you solve this psi n, you get a solution, and then it jumps back to a different solution, and it keeps jumping between two solutions. And so when this happens, you can use a slight trick to blend or slow down this oscillation. And this is done by essentially taking a weighted average between the solution, so psi n plus 1, and the previous value. So we just say that the psi n plus 1 is modified and just becomes some constant alpha times psi n plus 1. And this would occur in this stage here. So after solving for psi n plus 1, we then take a weighted average between psi n plus 1 and its previous value. So alpha here, of course, is either, it must be less than 1, or if it's equal to 1, then we just go back to the original problem, and greater than 0. So alpha in some range there will take an average of these two solutions. This reduces oscillations, but it can also slow down conversions. This is the basic scheme, but in order to invert this operator, so this is the elliptic operator, we need a boundary condition, and so we have fixed boundaries in this case. So we choose some shape of the plasma. So this is the plasma shape we want for some reason. On this surface, we say that B dot normal vector is 0. So there's no component of B out of here. And because we can write B as always grad psi cross grad alpha, where alpha is some other flux function, this means that therefore grad psi must be constant on this surface here. So the boundary condition is relatively straightforward in this case, that we just specify a shape, and this could be a set of Fourier harmonics, for example, and on that surface we can just write that the normal is just normal vector is proportional to the gradient of psi, and psi is constant on that surface. So then finally we come to the coordinates and how this is solved. So because we have a relatively simple geometry, there's no x points or anything, we can use a relatively simple coordinate systems, but we can use the coordinate systems to try and align the grids with the magnetic surfaces, and to get higher accuracy. So typically what's done is we have a magnetic axis here, we have a boundary shape we've specified, and then we choose, for example, you could choose just geometric angle. So there's an angle kind of theta going around in this direction, and then of course psi going outwards. And then we divide up this region into grids, which may look a bit like this. So we divide it into grids, so we end up with grids which have this shape. And so we have regions of the grid which look a bit like this. So we have a grid which consists of curved surfaces. So it's cells which are curved, and the edges are curved. This is needed because if we had just a straight edges, so if we try to make this just a straight line here, what would end up happening is that the shape of these cells are not aligned to the shape that we wanted, and this will lead to a loss of accuracy. So you'll need lots of cells to represent a curved shape, whereas if the cells themselves can be curved, then this leads to a more accurate solution, and you need fewer cells to represent the same accuracy of solution. And so what will happen is that we choose some cells initially based on this geometric angle. We solve for potential, and what we'll probably find is that the magnetic axis here is not where we thought it would be, so it'll be shifted somewhere, and then we can reuse that to create a new grid, interpolate from the old grid onto the new grid, and then progressively make our grid cells more aligned to the magnetic field. Okay, so once we have these cells, we need some way of calculating a solution on them. So one way is just to use finite differences, so we could use these points. So we've got points here, so we can take gradients. So you take these points here and take radial gradients, or these points here and take gradients in theta. The more accurate solution, and the one that's done in codes like Helena, is to use finite elements. And the idea is to represent inside this region here, we represent the solution psi as a combination of different basis functions. And the way to do this in a systematic and reasonable simple way to implement is to have a mapping from this curved surface. We need to map mapping onto a square. And specifically, they use a unit, well, go -1 to 1 or 0 to 1. So we have a standard size square. So in some normalized coordinates r and s, so this might be here, this might be r, and this might be s. So s is this distance around here, and r is this over here. And so we normalize this. So we have this might be some function of r, and this might be a function, say alpha of s. So there's a mapping from this real space onto a normalized space of r and s. And then what we can do is define this mapping so that the shape of the plasma is what we want. So we can define the shape of the plasma in major radius and height as a function v of our coordinate r, where v goes from 0 to 1. So 0 is the axis, and then 1 is the edge. We then have some shape, and this is the shape that you want on the outer boundary, times sine and cos to get the shape of the plasma. So this is the shape. And so this defines the shape of the outer edge of the plasma, and then of course this is some function of s. And this is called an isoparametric mapping. So we have a way of taking each cell, putting it through a map to get from the shapes into a unit or a standard square domain, and then inside this domain we have a solution psi, which is a function of s and r. And this solution psi we write as a combination of basis functions. So we write that psi, this function of s and r, is some combination of some kind of weighting. This is a weighting factor psi, which depends on the cell, and is some function of some set of basis functions s and r. And then what's done is that this is inserted into the Grashofanov equation, and you write that the integral or the volume of our so-called test functions, which here are the same as the basis functions, which is called the Galerkin method, but can in principle be different, multiplied by what we want to solve. So there's some function of psi. Integrate the volume is the integral of the volume of, again, our test function times the right hand side. So it's called the weak form. So you essentially multiply through by a test function, integrate over the volume, and then by inserting this solution here into this equation here, you can turn this equation into a linear problem, because all these coefficients you can take through the derivatives, and so you end up with terms involving derivatives of the basis functions. And then there are many different choices you can make. So a typical choice, for example, is that this is Hermite. Hermite polynomials. but for example in 1D, just because it's easier to plot, this might be S, for example, going from -1 to 1, and so in our cell like this, representing psi and these basis functions. So you might have one which is linearly decreasing. So this might be, that might be psi 1, for example. That might be psi 0. And this would be a linear basis function. So we just said that the solution is some combination of these two functions. You might then have higher order polynomials. So you might have quadratics or cubics. And in general, it's nice to have a set which is orthogonal. So Hermite, for example, is used in Helena. And having chosen your set of basis functions, inserted this into this weak form of the equation, you end up with essentially a linear algebra problem. So this left-hand side becomes a matrix. So this becomes a matrix which depends on these psi I. So you get a vector of these coefficients. So these are the coefficients in here. And there'll be a coefficient for every polynomial and a coefficient for every cell. And then here you end up with another vector on the right-hand side, which is a vector here. So you end up with a linear algebra problem or matrix inversion problem. And this you can solve using either iterative or direct methods, but various standard solution methods. So that's the basic idea of the finite element method used here. So you write in terms of basis functions. You put these basis functions into a standardized cell, and then use a mapping to map the standard cell into a curved cell. And the combination of these curved cells you make into a domain like this. And this method enables you to have very high accuracy solutions. So you get very good conversions and get very highly accurate solutions with relatively small number of cells.